Yo, chemists, ready for another time? Here's our game plan for today. We're going to go over homework. If you remember right, that was 1 through 3. Should have taken you, about 2 minutes. All right. I got the meat of the lesson. Remember, we are doing nuclear. Okay, so if you glow a little bit, that's all right. We want a little glow in life. Makes you look good. And then we will have some homework. And I'll just tell you right up front, it's problems 4 through 7. All right, that's our game plan. So let's start off this, though. All right, you ready for a joke? So I just saw a music video for radiation. If you think fighting stuffed animals is weird, imagine dragons. Okay, that was lame and stupid. All right, let's go over the homework. If anybody's laughing, you're going to lose points. All right, it said classify the following as ionizing or non-ionizing. Do you remember many moons ago we did the electromagnetic spectrum? Okay, way down here was radio. All right, micro, infrared, visible light, UV, X, gamma, cosmic. Did I get them all? Doesn't matter. Okay, doesn't matter. Right about there. From that point down, those are basically non-ionizing. There's not enough energy to cause any dilemmas. UV kind of bothers me a little bit, but they're just considered lower energy and all's good. From this point up, all right, they have enough energy. So this point up, they're ionizing. They have enough energy. They can cause change. Okay? So like infrared, non-ionizing, because it's below the magic point. Gamma's right there. What am I thinking? Gamma's not there. Gamma's right there. Ionizing. Micro, non-ionizing. I know mom says don't stand in front of the microwave while it's cooking. It's probably best you don't do that. Okay, but who knows? Okay, somebody try it and let me know. Okay, so I need somebody to stand there for 14 hours a day for 10 years and then report back to it. Maybe not. Okay, I don't really like UV. I'd like to leave UV out of all of our discussions because some say non and some say ionizing, so it can go either way. Okay, I think there's a borderline right in the middle. X-rays, ionizing. Radio, non. Alpha, ionizing. Beta, ionizing. Okay, I taught these two yesterday. Okay, moving on. Contrast ionizing and non-ionizing. Ionizing has enough energy to cause change. Okay, it hasn't. That's a key word here, is enough energy. That's ionizing. Okay, change means to ionize. You're going, what? Many moons ago, we had the word ion. Ion means you are a charged particle. Okay? So you can take this chunk of something and you can hit it with ionizing radiation and you'll end up with charges, positive and negatives. Okay, that's what ionizing means. It ionizes it, makes positive and negatives. Okay? Non-ionizing radiation is not enough energy to cause change. Okay, that's your radio. Go ahead and sleep next to your radio. All right, feel free to turn the lights on and not worry about much. Okay, now down here it said list the ones that originate from the nucleus. Well, if it's ionizing, we generally say it originates from the nucleus. So we have gamma rays, X-rays, alpha, and beta. And I'm just throwing UV out. Remember, I don't want to talk because somebody will say, well, he belongs, and some say he won't. So let's just throw him out. But all of these are the ones from up above on number 1, and all of these originate from the nucleus. Therefore, they're all ionizing. Okay? Homework. Done. That should have been a piece of cake. All right, I want to backtrack for half a moment. I want to go backwards. I already told you radiation. If you might want to stop the video, pull out your notes, and get ready. Homework's done. Guess I got to slow down. I got to remember people are moving papers and stuff. Okay, so stop the video, get your homework out. Not your homework, your notes out, and let's go. In your notes, you saw the one something that said radiation. Okay, and we said you don't even need to write. That's energy emitted, energy that comes from a source, the lights, and travels through space. Okay, radio, lights, all that garbage. Well, I want to take a step further. I want to look at the word radioactivity. This one, yo homies, put in your notes. Okay, radioactivity is spontaneous. Can never, I do it every time. If it's two N's or one M, emission. Okay, spontaneous, just happens, just boom, out of the blue. Emission, that means something's given off, okay, of radiation. So just out of the blue, all of a sudden, this radiation, this energy that's emitted, okay, all of a sudden it happens, but this time, from the nucleus of, gotta get my head in the game. So this atom is just sitting there. Its life is perfect. It has a bowl of ice cream, its favorite TV program on, a blanket on, a sunbeam on it. It cannot get any better than this. Then all of a sudden, out of the blue, something just flies out of the atom. Okay? That's radioactivity. It just flies out. Now, that atom that was sitting there all perfect with the ice cream and everything, and now it's changed. It's not the same atom anymore. I mean, come on, when your spleen flies out, you're not the same person anymore. Okay? So that's what radioactivity is. I mean, these atoms, you can't really just predict it and go, watch this right now, and then it's going to fire out. It's more of a spontaneous thing. Now, still going backwards, and we've already done this, but you may want to redo it. You had this on a test, and if I stopped and if I were able to pick on somebody right now and say, you, there in the third row, yeah, you, Torin, you know who I'm talking about. All right, if I said, what's an isotope? I think some of you would look at me and go, huh? Isotope is an atom that has more or less neutrons, okay? Means it has a different mass. It's kind of, to me, it's like a little bit of fat. We all have a little extra fat, okay? As the day goes on, we gain weight a little bit because we eat more. We're an isotope of ourselves. And then in the morning, we probably weigh our lightest. So we're an isotope of ourselves again. So basically, it's an atom who the weight goes up and down, but the key is it's the neutrons. Okay? Now, I know it's like all these pieces coming at you, but it's going to fit together. So think about radioactivity, stuff flying out. Okay, isotopes, more or less neutrons. If you did a graph, okay, and you had the number of protons right here, and the number of neutrons. All right, so you're talking about all the different elements, and if you look at how many protons they have versus how many neutrons they have. Well, if you do this, remember directly proportional? Directly proportional, that line right there signifies a 1-to-1 ratio. So if I have 27 protons, then if I'm on that line, I would have 27 neutrons. Okay, so that's a 1-to-1 ratio. Now, the elements on the periodic table tend to do this. If you actually look at their number of P's and number of N's, kind of starts out and then it kind of veers away. What it's saying is, as we go down the periodic table, they tend to have a few more neutrons than they do protons. Now, generally, if you're on this line, you are considered stable. Remember that atom sitting there eating its ice cream, watching its favorite TV program? Well, if you're on this line, you'll just continue to eat your ice cream and continue to watch your program and no changes. Okay, you're just going to sit there nice, perfect, and happy. If you go basically on either side of this line, okay, it's like a shadow region. If you go on either side of that line, basically you'll become unstable, and what they'll say is you'll become radioactive, which means all of a sudden something fires out of you. There goes your spleen. There goes a kidney. Okay? So line of stability, boom, 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 on either side, which means maybe you have more neutrons or you have less neutrons than this line, you become unstable, okay? And you become radioactive. All right, now there's a thing out there called the chart of the nuclides. Remember, nuclide's another way to say the nucleus. And you can say like the uranium nuclide. Okay, we're not talking about the electrons now. We're talking about the middle of the atom. All right, there's called chart of the nuclides. And it's a crazy chart. Okay, it's huge, 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 huge. And basically it shows the isotopes of all the elements. Remember, an isotope, you have more or less neutrons. More or less neutrons. So like carbon off the periodic table. Now that's one way to write it. You just write carbon 12. That 12 is his mass. The minute I wrote carbon, everybody in the world knows I mean 6 protons. You can't be carbon unless you have 6 protons. So a lot of times I write his mass. Well, there's a carbon out there. There's carbon 12. Actually, carbon 12 is stable. There's a carbon 13, so he gained a neutron. Carbon 14. If you ever heard of radioactive dating, a lot of times they use carbon 14. Okay, maybe there's a carbon 15. I don't know how many are possible, but there's a lot. Well, there could be a carbon 11, a carbon 10, a carbon 9. This goes kind of with that last graph I showed. Carbon 12 is considered somewhat stable. And as you veer away from carbon 12, these nuclides, these isotopes, tend to become more radioactive. They are unstable because of their ratio of protons and neutrons. Okay? Now this chart, I've only picked carbon. On this chart, you'll see like above it is nitrogen 13, nitrogen 14, nitrogen 15, 16, nitrogen 12, nitrogen 11. I'm not going to do it all. And basically, I should have drawn this line a little more like this. That's the line of stability. As it goes up, nitrogen 13 tends to be pretty stable. Maybe nitrogen 14. Right around that region. So anywhere on this line or near it, you're considered stable. And as you go further away, you are unstable. And this chart, I mean, I only did carbon and nitrogen. You know, if you go below it in all the various elements, this chart just is huge. And it starts way down here with hydrogen. And there's only a couple hydrogens. But as the chart goes up, it tends to branch out and get bigger, 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 bigger. And I mean, you get up there in the very big elements, heavy elements, and the chart's just amazingly big. Okay, so that's all part of the radioactive stuff. Okay? Now, you and I are constantly receiving radiation. Yep, you're sitting right there and you're getting bombarded with it. So am I. It is what it is. Some of the sources, okay? Some of the sources for this radiation that you and I receive, okay, is Earth itself. I don't care how you believe, God, Big Bang, Buddha. Hold on to your beliefs. That's what I totally dig. Hold on to your beliefs. But somehow, Earth itself, some of the materials, the granite and various other things are naturally radioactive. They are what they are. The Big Bang, God, Buddha, they put them here somehow. Okay? It just is what it is. An example. If you live in Connecticut, all right? Mascot of the basketball team from the University of Connecticut. Name it now, go. Crap, I just forgot. Girls basketball coach. They win all kinds of national titles for Connecticut. Ready? Name it. Don't know. In Connecticut, they have an abundance of radon gas that collects in the basements of their homes. It comes from the soil naturally. Radon gas is radioactive. Okay, it just happens to be in Connecticut. Radon gas emanates from the soil, and it tends to collect in basements because a lot of times basements, we don't have a lot of airflow. They kind of get shut up. And in Connecticut, 1 in 5 homes, 1 in 5 have trouble with radon gas, which is radioactive. Okay? If you lived in Grand Central Station in New York, okay, if you live there, which you can't live there, that's, I think, where they go to get the subway trains and all that. I've seen it. Absolutely amazing. If you live there, you would pick up an additional 570 millirems in a year. Now you're going, what's a millirem? It's a way of measuring radiation. And you're like, well, is that a lot? Will that hurt me? If you go to the doc, okay? Yo, doc, what's up? Isn't that what Bugs Bunny says? Sorry, I digress. All right. A chest x-ray. Now, I know people say all kinds of numbers, but give or take 10, 20 millirem. So if you go to the doctor and get a chest x-ray, 10 to 20. If you get your tummy looked at, an x-ray for your tummy, that's about 70. That's how you shorten millirem. You may not know this. If you fly from LA to New York, because flying means you go up higher and you go closest to the largest source of radiation we know. The largest source of radiation we know is the sun. So when you fly, pilots, Mr. Spencer's son is a pilot, he will actually pick up more radiation than I will. All right? So LA to New York is about 2 to 5 millirem. So I really wouldn't worry about that too much. Okay. Another place that you and I get bombarded with radiation in our normal life, food. Okay. One of the biggest sources are bananas. Never remember which letters to double. So if hold on, we gotta double this one. If I double them all, we're good. Bananas, if you remember, if you've been on break, K is potassium, 40 is his mass. Potassium 40, that nucleide tends to be radioactive. It's in bananas. You're eating it right now. Should you worry? Heck no. Gobble 4 or 5 bananas. It's not going to bother you. Okay? It's not going to bother you. All of this radiation in your normal life, all of this stuff is called background radiation. Now, the government can set a number and say you shouldn't exceed this, but normal people will not exceed it. And background radiation changes according to where you live, what you eat, and what kind of job you have. But it's just out there. It's just facts of life that we deal with. It's just background radiation. It's all there. Okay? All right, types of decay. So now I set us up. I'm talking about all this radiation, this stuff flying out of the atom. I want to look at it a little closer. All right? So that atom that's sitting there eating its ice cream, watching a TV program with its blankie, the sunbeam on it, okay? We'll just call that the thing you start with. We'll call that happy atom. Okay? The thing you start with is called the parent nucleide. Now, all of a sudden, the proton to neutron ratio ain't proper, okay? And something flies out, all right? So remember the things I told you yesterday that potentially could fly out? You could have an alpha, a beta. Remember beta was beta positive, beta negative. Beta positive we call a positron. You could have a neutron. Lots of things could fly out. Okay, lots of things could fly out. Well, once that little bitty piece flies out, whatever is left over is called the daughter nucleide. So you're sitting there happy, boom, your spleen flies out, whatever's left, that's the daughter. Now, I think it's kind of sexist. There's only daughters and parents. There's no sons. That ain't right. Okay? That ain't right. Don't dig it. Okay, so as we talk about this, let's look at alpha decay. Okay, remember alpha is a helium nucleus. It's positively charged. Remember its nuclear symbol was 4/2 He. So now there's certain elements out there. Th is thorium. And thorium-230. Remember the 230 is his mass. That's his P's. Pardon me. His P's and his N's added together. Now on a periodic table, thorium normally weighs 232.038. Okay? Don't worry about that. This guy's slightly different. He's an isotope. So the way we do this is we take thorium. Mass goes on top. I looked him up on a periodic table and he's number 90. So that's his mass. Okay. That's his atomic number, his number of protons. So that right there is the parent. Now he's sitting there and all of a sudden he doesn't feel very good. And if they say alpha decay, this alpha particle goes pew, flying out of him. You can't see it, you can't smell it. We do have devices that can register it, but it's more like a click on a device versus anything we can see or do. Here's how this works. See that? Think of that as an equal sign, and all this is a math problem. So see over here, we got 230. 230 equals 4 plus what? Well, it'd be 226. 226 and 4 is 230. Down below, this is 90. 2 plus what equals 90? 88. Now I go to the periodic table and I have to look up number 88, and it's radium. That is called an alpha decay or an alpha emission problem. Alpha decay. Now remember alpha, sometimes they write it like that. A fish swimming to the left. That's not a very good one. That's a better one. Okay? So that's alpha decay, alpha emission. There's your parent. There's your daughter. Let's try one more. I want you to stop the video and do the alpha decay for plutonium-240. Stop the video, do it, write the equation, and then start it back up. 240, and then I looked up plutonium. It's 94. Pu, smell your armpit. Okay. All of a sudden, alpha particle comes flying out. Pew! What's left? 236 and 4 is 240. 92 and 2 is 94. And I go to the periodic table, and I look up 92, and that is uranium. Okay? That's alpha decay. I want to get in beta real quick and neutron, and we're done. Okay? Beta decay. Or beta emission. Remember, it was the B with the tail. Beta negative, which is 0 mass, -1 charge, and it's an electron, a high-speed electron. That's beta negative. Beta positive is called a positron. Okay, everything works the same. So if they gave me magnesium, 27/12, and they told me to do beta negative. Okay, some people don't like this. 0 plus what is 27. Here's the part you don't like. 12 equals what plus -1? What plus -1 equals 12? It's 13. It actually goes up. Beta negative decay actually goes up, and that's aluminum. If I show positron or beta positive, Well, it's 14 on top. Anybody and their dog can do that. And this time, it's 7. 7 plus 1 is 8. It's nitrogen. Okay? Hang in there. I know this video is a little bit longer, but it's what we got to do. Okay? Neutron decay is slightly weird. I won't give you homework on this. I'm setting this up for a future thing. All right, so there's some elements out there like californium. You probably never even seen that one. Don't quote me on this, but I think it was discovered at the University of California at Berkeley. Okay, that's why I call it californium. He is radioactive naturally. Okay, he's unstable. He's got that bad ratio that we talked about. All right, now with sometimes a little bit of help, and we'll talk about that later, how he gets a little bit of help, but he undergoes a radioactive process, he decays, and you get these weird things. So you may get some palladium. So in a sense, he's split apart. Now you don't always just get that. It's the idea here. And then you get some neutrons given off. Now notice I said plural. So if I add up the top, 118, 132, that's 0, carry the 1, that's 2, and 3 is 5, 250. See how I'm 4 short? I need 4 of them. Okay, 4 neutrons, 4 little particles go pew, 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 pew. And that'll be important later. Okay? The last thing I got to show you is sometimes they like to be weird and they like to do this. Okay? They give you a nuclide. Okay, they give you iodine. There's your parent. There's your parent. They give you the daughter. And they say, who be? Okay, who goes there? Well, I can see 124 and it's 128, so that means it's a 4 on top. 51, 53, that means I need a 2 on the bottom. Some of you go, well, who's 4 over 2? The answer is alpha particle. That's the answer. Okay? Tonight, I'd like you to try on my website, open the folder labeled Nuclear Chemistry. Okay? And I'd like you to try problems 4 through 7. All right, peace out.